Depth of incorporation. You don't have to get it in very deep. Any tillage tool that's going to be used, any secondary tillage tool, a disc, a field cultivator will be deep enough. A rotary hoe, probably not as good as we'd like to see, but it would help because you're going to get more mixing. But a disc or a field cultivator will do the job, and it will take it in for us. Moving on, ammonium nitrate, a product we don't have much of, and unfortunately because of the accident last week, we're going to have less of it in this coming year, by a little bit anyway. It is an excellent nitrogen material in that it is not volatile. You can put ammonium nitrate on top of the ground and it will not volatilize. You can leave it lay there. But when you look at the two compounds that are in ammonium nitrate, it has half of its N as ammonium, NH4, and half of it as nitrate. What is the biggest loss mechanism that you can imagine from that product? Leaching or denitrification, because half of that N is nitrate. So half of that N is susceptible to those two loss mechanisms the minute you put it on the ground. Now, over time, if you're comparing different fertilizer products, compare ammonia against ammonium nitrate, and the two have been on the ground for a month or in the ground for a month, there's not going to be any difference in them in terms of the potential for leaching or denitrification. But if you're talking about putting that product on and getting excessively wet right afterward, ammonium nitrate has the highest loss potential of any of the materials that we'll use. Ammonium sulfate, again, an excellent fertilizer material. It is non-volatile. It will not volatilize. So you can surface apply it and let it lay there. The problem with ammonium sulfate, it is more acidifying. It is going to take more lime to correct the acidity from ammonium sulfate than from any other nitrogen material that we have. The figure that's commonly used is it takes 4 pounds of agricultural lime to correct the acidity of 1 pound of nitrogen fertilizer. That's true for ammonia, for urea, for UAN solutions, and for ammonium nitrate. But for ammonium sulfate, it will take about 8 pounds of lime to correct the acidity from 1 pound of nitrogen as ammonium sulfate. So it is far more acidifying than is the case with any of the other N sources. The advantage that ammonium sulfate has, besides being non-volatile, is if you have a sulfur problem, it's an excellent sulfur source. But if we don't have the sulfur deficiency, then that really doesn't play in or count very much. Now, we do get acidity created by the application of nitrogen. We talked about that earlier. It comes in 2 ways. One is the conversion of ammonium to nitrate. The nitrification process releases hydrogen. If you look at ammonium, it's NH4. It has 4 hydrogens with every nitrogen. When you convert to nitrate, those 4 hydrogens are not there. It's NO3. So you release 4 hydrogens for every nitrogen molecule that you have in that compound. And we also get it because of the leaching problem. When you leach a cation or an anion, if you leach nitrate out of the soil or you leach sulfate out of the soil, to maintain neutrality or electrical neutrality, a cation is going to go with it. That means you're going to take some calcium out of there. And that will result in an increase in soil acidity as well. What's the function of nitrogen? And you need to know the function of most of the nutrients that we're talking about. What's the primary function of nitrogen? It's a part of the chlorophyll molecule, therefore it is a part of photosynthesis, the plant manufacturing mechanism. Nitrogen is a part of the proteins. It's a part of amino acids. When you get an increased nitrogen content in the plant, most often, or in many plants, you'll get an increase in protein content. That's not always true. With corn, quite often, with the highest yielding corn varieties we've got, we actually get a decrease in protein. Normally we get higher protein under lower yielding situations. But those are some of the mechanisms that nitrogen is involved with. You need to know nutrient deficiency symptoms, and at the end of the program, if I get moving here quickly enough, we're going to get to the nutrient deficiency symptoms for all of the elements. Nitrogen is going to start at the tip of the leaf, and it's going to move down the midrib. Now, the way I remember nitrogen is N for nitrogen. It's on the inside of the leaf. Now, potassium is also going to start at the tip, but it's going to move down the margins. And the way I distinguish that from nitrogen, it's okay for potassium. On the outside for K, on the inside for nitrogen. N for nitrogen, okay for potassium. Now, in both cases, for nitrogen and potassium, the deficiency is going to occur on the lower leaves, on the older leaves, and will move up. What does that tell you about that nutrient? Is it mobile or immobile? It's mobile. When the deficiency occurs on an older leaf, but does not occur on the new leaf, it means the plant is remobilizing. It's taking that nutrient and moving it into the new tissue. So again, remember that, because that gives you a clue as to the mobility of nutrients. Nitrogen deficiency, we've all seen it. Slow growth, the yellowing on the leaves, yellowing on that midrib, later maturing. Okay, phosphorus. And we're going to move through the rest of these elements quite a bit faster than we've moved through nitrogen, or we would be here till mid-afternoon. Phosphorus is taken up primarily as HPO4 or H2PO4. Both of those are an anion. But as I said earlier, it doesn't leach. Because at any point in time, you're not going to have very much of that HPO4 or H2PO4 in solution. It'll only be a small amount. I think it's a good thing that that's the case. It's a mechanism that helps preserve that phosphate so that it gets into the plant and doesn't leach and get into groundwater. In terms of mobility, phosphorus basically doesn't move. Nitrogen, of course, very, very mobile. Potassium, a little bit of mobility, but not much. But phosphorus just simply doesn't move. If you put it on the soil, it's going to stay where you put it. Now, when we look at phosphorus, I like to liken the phosphorus reactions to a horse tank. For those of you that have grown up and been around livestock, you know what I'm talking about. That horse tank fills to a given level, and then the float closes on it. And when the cattle come up to drink, they take the water out, the float drops, and more flows in. Now, if for some reason it overflows, you've got another pipe that'll let it drain off onto another storage tank or drain out somewhere else. Now, if we look at phosphorus in that same light, we've got our solution phosphorus, and that's what the plant uses out of. And that's what I'm talking about, the horse tank. That horse tank is pretty small in storage compared to the amount of water that's in the ground, isn't it? Well, the same is true here with solution phosphorus. The amount you have in solution at any point in time is very small compared to the total amount that's there. Now, that solution phosphorus, the amount that's in that tank, we get it from fertilizers. We get some flowing in there. When we put fertilizers on, most all of the fertilizers we use are highly soluble. And they'll dissolve and go into solution. But they don't stay there very long. There's this overflow pipe that kicks it out. If we're on calcareous soils, high pH soils, it goes out as a calcium phosphate. If we are on acid soils, then it comes out and is precipitated out as an iron or an aluminum phosphate. Those are insoluble, or relatively insoluble. And what happens when that corn plant starts to use it, or that soybean plant, or whatever kind of plant we're growing out there, starts to use that phosphorus out of the tank, it triggers the mechanism. It's a reverse, or the reverse reaction. And those phosphates that have been precipitated, some of them will resolubilize and come back into the tank and just keep us with a steady supply. But because of the fact that we have very little in solution at any point in time, we don't have a leaching problem. It doesn't move because there's just very little there at any point in time. What is phosphorus responsible for in the plant? Like nitrogen, it's involved in the photosynthesis reaction. It's an energy transfer mechanism. It's involved in cell division. But if you want to keep one primary thing, it's involved in the photosynthesis reaction. That's the one that I would key in on. What affects its availability? Obviously, the inherent soil test, or the inherent amount that's present in that soil at any point in time. Tillage can affect it in terms of its availability. As we said earlier, if it doesn't move, you're going to find it all up in the top with what you put on. If your rooting system is getting its water from down deep, then even though you've got plenty of phosphorus there, it's not able to use it. So tillage can influence the amount of phosphorus that is available at any point in time. Phosphorus fixing capacity, when we get onto high pH soils, we get fixation occurring that's not as easily reversible. And on those soils, we're better off to band apply our phosphorus because the rate of recovery of broadcast phosphorus is very, very low on those high P fixing soils. But primarily, we're talking about high pH. pH is a 7.2, 7.3 and above. The phosphorus fertilizers that we have all come from one place, rock phosphate. That is the source of all of our phosphorus fertilizers. We simply then run them through the process. We used to have a material called O20O, the old normal super or ordinary super phos. Very little of that in the marketplace. One advantage that that material had was it had a high sulfur content. So if we got into areas that were sulfur deficient, we were getting a good supply of sulfur as well, except that we're paying the cost of shipping that sulfur. And because of that, the industry shifted from the old O20O to O46O, triple super. The difference between O20O and O46O is they acidulate with phosphoric acid instead of sulfuric acid. So you don't have the sulfur in there anymore. It's just, it's very clean. A little bit of phosphorus, but not very much. Put ammonia with it, with the triple, and you're going to form MAP or DAP. Both of those compounds highly water soluble. And that 95+% water solubility. Now that is one thing that we do talk about is water solubility and its influence on availability. And I got ahead of myself, we'll get to that in just a minute. The other thing in terms of materials is ortho versus polyphosphates. Polyphosphates are simply a combination of orthos. If you'll take that ortho up at the top of the slide, look at that structure. Now pick that up and bring it down onto the poly. And look at the left side. They're identical, aren't they? Except that where you've got an OH on the right-hand side of the molecule on top, when you get down into the center, it just has an O. Now if you pick another one up and bring it down, and put it on the right side over here in the poly. Again, if you look at the structures, they're identical, but again, all you have is an O on the left side. And up above, you've got an OH. So if you take that one that's up above and say that you're going to put two of those together, and that's what you get on the bottom, what's the difference? You've taken one hydrogen off and one OH off, right? What's HOH? Water. All you've done to form poly is pulled water out of it and tied them together. It's a polymer. And you can put all kinds of them together. We're just showing you two of them here, but you can put long chains of it together. Now, what does the plant use? The plant uses the Ortho, the PO4. It does not use poly. Why would there be an advantage then? Well, the advantage is in shipping costs because the poly has lower water content, higher percent P. When you put this polyphosphate back in the soil, it's going to take on water and it's going to go back to the Ortho. And the Ortho is what's going to be taken up. Now, as I indicated, water solubility is something that we think is important. And it is important, particularly on high pH soils. But of the commonly available materials that we have in the marketplace, they all have adequate water solubility as long as pH is below 7.2, 7.3. There is no difference in availability among those materials, basically. They suggest that we'd ought to be at least 60% water soluble. Well, every material we've got in the marketplace is over 80%. And most of them are up in the 90 to 95%. Now, when you get onto a high pH soil, then we would like to see them up in that 85 to 90% water solubility. Then they're going to perform better up at that point. This is a conversion that you'd ought to have in mind, to convert P to P2O5 or P2O5 to P. Now, you all know that on the fertilizer label, we report everything as P2O5. There is no fertilizer that contains P2O5. None. That's simply the way the chemists decided to report it years ago, is on an oxide basis. Now to convert P to P2O5, multiply by 2.29 or 2.3. Or conversely, to convert P2O5 to P, multiply by 0.43. Now personally, I can never remember those numbers. The way I remember them, this may seem strange, and for the younger ones of you, you may have more difficulty than I do with it. But if we were to sell today on the basis of P rather than P2O5, what is currently marketed as 046O triple super would be marketed as 020O, which was the percentage on the old ordinary super that we had years ago. So 046O becomes 020O if you were to convert it. And you can go back through that calculation and figure out what that conversion factor is. Potash is a cation. It's taken up as a cation. And it is held in that soil complex. It's held on the exchange capacity. What is its function? Well, as they say on here, it's vital to photosynthesis and other metabolic functions. To be very honest, most of us don't know what it does in the plant, why it's essential, but we know it's essential. K deficiency, as I pointed out earlier, is on the outside of the leaf. Okay for K, on the outside of the leaf for K. It's going to be on the older leaves, which again means it's what kind of a nutrient? Mobile. Now, quite often when you split the stalk, you're also going to find a darkening of the internodes on corn. That's a characteristic symptom of K deficiency. There are three forms of potassium. Well, there's probably many, many forms, but we've broken them into three separate ones. The available, starting on the bottom, slowly available, and the unavailable. Now, what do we mean by that? Well, again, if we go to a sort of a schematic of it, the available means that's in solution, that's in the soil solution. Again, you're going to have fairly small amounts in solution at any point in time. In addition, that is on the exchange is fairly readily available. That will come off fairly quickly. The slowly available is what we get trapped in those soil colloids, in between the clay particles, the quote fixation. And the unavailable is that's in the minerals and rocks. Now, there are groups of people that say we've got, probably 20,000, 30,000 pounds of potassium in the soil. Why in the world are we buying fertilizers? Why don't we simply find a way to release that? And in fact, there are some companies say they've already got that. I'm not sure it quite works, but they say they have it. But is that really what we want to do? Do we want to dissolve all the minerals and rocks out of our ground? We're going to get subsidence, aren't we? The ground will shrink around here. It will go down if we use up all of that. Now, I think we'd really best off to continue to use out of the readily available and the slowly available sources that we've got out there. Sources of potash, the primary one's KCl. Not only does it give you the potash, the K, it gives you the chloride as well. One of the reasons we never have chloride deficiency in this state is because we're getting plenty of it with our potash. If you have a sulfur deficiency, potassium sulfate is an excellent source. Now, KCl, 0060, or 062, whatever you want to call it. Potassium sulfate is 050. It's a little lower in the K content, but it does have the sulfur with it. If you're talking about sulfur deficiency on alfalfa, that's probably one of the best materials you could use. Potassium magnesium sulfate, if you had the deficiency of all three, this is an excellent source for them. But if you don't have all of those deficiencies, then the added cost really can't be justified. Potassium nitrate, a material that is used primarily in high-value crops, things like tobacco, crops where they want a low salt index. Then they will use potassium nitrate. It is entirely too expensive of a material to be used in the agronomic grain crops area. Potassium is not held tightly in the plant at all. It is very, very soluble. As soon as that plant dies, in fact, I guess I'm fairly well convinced it's even before the plant dies, if you get water moving across that tissue, that potassium is going to leach out. That's one of the reasons we see some of the cyclical nature of potassium in soil tests, is as soon as that plant dies and gets rained on, and that residue gets rained on, it's like putting fertilizer out there. That K is going to come out of that tissue very, very readily. Okay, let's move on into the secondaries. Calcium. As I indicated earlier, calcium deficiency is one that seldom ever occurs throughout the Corn Belt, unless you have extremely acid soils. And I'm talking about pHs down in the 4 to 4 or 5 range. Calcium, of course, is the most dominant cation on the exchange. It's present in rather large amounts, and it's consumed in fairly large amounts in the plants as well. But we seldom ever see a deficiency because we maintain that pH at the level where we're going to have a large amount of calcium around. What does calcium do? Well, it's involved in cell elongation and division, part of the cell membranes. And when we look at calcium deficiency in a little while, I think you'll clearly see that when you have the deficiency, it's a breakdown of that elongation, a breakdown of cell division. Magnesium, It's most often going to be deficient also on acid soils and most often on sandy soils. And most often in areas where we're using calcitic rather than dolomitic limestone. Dolomitic limestone is calcium and magnesium. Calcitic limestone is calcium carbonate. So the places we're most likely to find it are on acid soils, sandy soils, and in areas that are using calcitic lime as a liming material. This slide says on high potassium soils, to be very honest, while that may have an impact, we've never really been able to identify that the high potassium levels are going to create a magnesium deficiency. They may reduce magnesium uptake to some extent, but we've never seen it create a magnesium deficiency. Magnesium is a part of the chlorophyll molecule. Very, very important in the photosynthesis process. And as a result, when you see the deficiency, and I think I've got a shot of that in there, you're going to find some yellowing. You're going to find intervenal chlorosis, yellowing between the veins, and for the most part, the veins are going to stay green. Now that is true with almost every secondary and micronutrient deficiency symptom, is intervenal chlorosis. Not quite all of them, but almost every one. That is one of the symptoms. With magnesium, the leaf will turn a maroon or a purplish color as well. Sources of it, well, the easiest source, if you have an acid soil, is dolomitic limestone. But if you don't have a ready supply of dolomitic limestone, then you can use calcitic limestone to correct the acidity and go to some of the other magnesium fertilizer materials as a source of the magnesium. Potassium magnesium sulfate, sulfomag or K-mag materials are an excellent magnesium source. Epsom salts, magnesium sulfate is another excellent material. Sulfur. Plants take up as much sulfur, as I indicated earlier, as they do phosphorus. Sulfur deficiency on alfalfa will occur when the level is below about 0.2% S. That's about the same break point for phosphorus. And oftentimes you'll find 0.3, 0.4% sulfur in the plant. So there's as much there as there is with phosphorus. It's taken up as a sulfate ion. Sulfate is what? Anion or cation? Anion. And as a result, it's readily leachable. Sulfur can also be absorbed directly through the leaf as the SO2 gas. Sulfur dioxide. Now, sulfur dioxide is very toxic. If you get high enough concentrations, it'll kill plants. But it can be a rather significant source of sulfur in some areas. In a deficient state, in some of the work we did many years ago, we could get as much as 70 to 80% of the sulfur taken up by the plant coming directly through the leaf as SO2 absorption. Now, it still wasn't enough to take care and alleviate the deficiency, but a fairly high percentage can come in through that leaf. When we look at the sulfur cycle, the primary source of sulfur is organic matter out of the soil. The mineralization, the breakdown of organic matter is the primary source of sulfur. We also get a significant amount of sulfur from precipitation throughout much of the Corn Belt. In fact, throughout much of the U.S. The smokestacks that are out there are emitting SO2. When that sulfur dioxide is emitted and gets into the atmosphere and gets into rain, it converts to sulfate. And it's brought down to the ground. Throughout the Corn Belt, in the eastern part of the Corn Belt, we're probably getting somewhere 25, 30 pounds of sulfur per acre per year during the growing season, just in the rainfall. That's what some call the acid rain, and it definitely is contributing to acid rain, but it is a real plus. It means we don't have to buy that fertilizer. At this point in time, it doesn't cost the power companies anything to give it to us, it doesn't cost us anything to take it. I think we ought to kind of let it go that way, but that's not the way it's probably going to occur. In fact, if things develop as it looks like they might, the power companies may be our next major source of nitrogen fertilizer. It's going to be ammonium sulfate. Now, they aren't going to produce the ammonia. They're going to buy it from somebody that's already producing it. They're simply going to scrub those stacks with that and form, with ammonia, and form ammonium sulfate. If that happens, and there's a strong move afoot now to try and get a process that will work, if it happens, as few as 10 power plants in this state would take care of the entire nitrogen needs. Now, the power companies don't want to be involved in the fertilizer business, so they're going to be still marketing it through you. You're still going to be the source of that supply to the farmer, but it could markedly change our marketing program in the future. Will it be liquid or dry? Most likely it'll be dry. There's just no way that we can handle that volume of material in a liquid state that I can see. Because storage, I mean, we're going to produce it 365 days a year, 24 hours a day, and I think it's going to have to be a dry form in order to be able to store it. They may market some liquid during the season, but the majority of it would probably go dry. But 10 power plants would take care of the needs of this state for all of the nitrogen that we consume at this point in time. I missed that, but how soon? I think we're probably looking at least, my guess is before it's a major factor, 8 to 10 years. Maybe not quite that long. In some areas, it may be a major factor before that. The first pilot plant will be built, I think, this coming year. It won't be built in Illinois. I tried to get it here, but it isn't going to be here. It's going to be somewhere else, and I don't even know where that's at. But then you're looking at probably a 2 to 3 year time period to test the pilot plant, and then if it works, by the time they start building and get it onto power plants, we're probably looking at another 3 years with the way those processes go on. It'll be competitive. It's going to have to be, or else it won't be in the marketplace. That's about all I can say. No, it'll actually go in as the ammonia gas, is my understanding anyway. Now, at this point, I don't know the full details. But it, not only will it scrub the sulfur out, but there's also nitrogen being emitted from those stack gases. And it will scrub that nitrogen, so it'll actually enhance the concentration slightly. Instead of being an 021, I mean a 2100, it'll probably run about 23 or 24% in. It'll pick up that much in. So I think it's interesting. I think it's an interesting concept, and hopefully the thing will work. It was tried once already at Indianapolis a few years ago, and it didn't work. But the process, the engineering has been redesigned such that they're convinced it will work this time. I hope it does, because it could be a real boon to several of us in terms of several of the industries, and allowing the power industry to scrub with something that's usable instead of just producing gypsum, which is about as worthless a product as you can produce in today's marketplace. It'll be about 23 or 24% in. On the sulfur will be about equivalent, just a little less. The sulfur will probably come in about 19, 20% sulfur. A lot more sulfur than we need, but not something that we're going to worry about. Okay, as I said, organic matter is the primary source of sulfur, in addition to that coming from precipitation. We also do get some sulfur from our fertilizers, particularly the phosphates. There's still some sulfur left in it. Sulfur is a constituent of protein. As a result, it's involved in photosynthesis. It's involved in a number of enzymes. It's necessary in the chlorophyll formation. Well, the fact that it's involved in chlorophyll formation, the fact that it's involved in proteins, would probably tell you pretty quickly what its deficiency is going to look like, wouldn't it? And that deficiency is an overall yellowing, particularly in alfalfa. In corn, you're going to see the deficiency in the upper part of the plant, and we will show you that a little bit later. You see the deficiency in the new tissue, the upper part of the plant. What does it tell you about its mobility? Immobile plant, or immobile nutrient. And that very definitely is the case with sulfur. Sources of sulfur, well, the ammonium sulfate that I just talked about is listed as number 1, but if you're talking about alfalfa, potassium sulfate or gypsum would be the better source there. Potassium sulfate if you need the K. If you don't need the potassium, then gypsum would be a far cheaper source of sulfur in most areas of the state. Elemental sulfur is also an excellent source, but it is not readily available at the time you put it on the ground. Elemental sulfur must be converted to the sulfate form. That is a microbial process. And as a result, it takes some time. My suggestion to people that are fertilizing alfalfa would be to use elemental sulfur and a combination of elemental and a sulfate. Sulfate for the quick reaction, elemental which will give you a slow release and one that you can count on for the next couple of years. Moving into the micronutrients. Again, there are 7 of them: boron, chloride, copper, molybdenum, manganese, iron, and zinc. If at all possible, remember the symbols for them as well. The 1 or 2 letter symbols, because there are probably going to be some of the questions written that are going to simply give you the symbols. Now, usually you can identify the symbol with the element just based on the first letter. Boron with the B is pretty obvious. Chloride, the Cl, is pretty obvious. Copper, Cu. Well, the U part of it isn't quite so obvious, but the C is certainly pretty evident. Iron, though, is a little tough to identify, isn't it? Starts with an I in the word and an F in the symbol. Well, that's because of the ferrous or ferric iron. That's where the Fe comes from. Manganese, Mn. Remember the difference between manganese and magnesium. Magnesium is a secondary nutrient, and it is Mg. Manganese is a micronutrient, and it is Mn. Molybdenum, Mo or moly. Zinc, the Zn. That one is fairly evident and fairly easy to remember as well. Again, most of the micronutrients have decreased availability with an increase in pH. And most of the deficiencies will occur when the pH is greater than 7.2 to 7.3. That's where the problems will start. And the higher that pH goes, the more likely you are to have the problem. The one exception is molybdenum. It is more available at a high pH, less available in an acid soil. The easiest way to correct molybdenum deficiency is a liming program. Boron, involved in pollination and germination. It's involved in the seed and cell wall formations. Those are some of the functions of boron in the plant. Now you can look at some of these functions and think of how the deficiency might occur, or conversely, when you remember the deficiency symptoms, it'll help you remember what some of the functions are of these various nutrients in the plant. We've talked about a lot of them that are involved in photosynthesis. Automatically, that deficiency symptom being yellow says that it's going to be involved in photosynthesis. It's going to be involved in chlorophyll formation. In the case of boron, cell wall formation, and when you look at the deficiency on corn of boron, you get this buggy whipping. Well, it's just that the cells haven't elongated. The cells haven't divided. So it's fairly easy to remember. Primary source of boron in soils is organic matter. Again, mineralization, the breakdown of organic matter, is very important in releasing boron into solution. Boron is taken up as an anion. Boron will leach. Where do you most often see boron deficiency? It's going to be on a sandy soil. For two reasons. One is because of the leaching. The other is the primary source is organic matter. Most often sandy soils are going to have low organic matter. So boron is most often going to occur on a sandy soil. That doesn't mean it's exclusive. You can see boron deficiency on alfalfa on some of the heavier soils. Alfalfa is the crop that will show boron deficiency first. Sources of boron, well, there's primarily one, the borax, the soluble. That's the primary material that's used, the primary material that's sold in this country. And it's an excellent source of boron. Copper, I personally have never seen the deficiency. Most often it will occur on organic soils. They do see it some in Michigan. Wisconsin has reported it some as well. But I personally have never seen the deficiency occur within the state of Illinois. Again, high pH soils, high organic soils are the most likely to show the problem. To correct it, if it's high organic matter soils, probably the copper sulfate is going to work pretty well. If you're on high pH, and this is true for most of the micronutrients, the chelated form is probably going to work better. It's an organic form or an organic complex. It resists fixation better than do the inorganic materials. What does copper do? Well, it's like most of the micronutrients, it's involved in many enzyme reactions. Involves some in protein and carbohydrate metabolism, and appears to be involved somewhat in the fixation of nitrogen, symbiotic fixation. Iron deficiency. Where are you going to see it? You're going to see it on high pH soils. Number one. It can occur or can be induced if we get an imbalance with other metals. Some work that was done a number of years ago, just a little ways north of here up into Wisconsin, when they put a manganese chelate on the ground, they could actually create iron deficiency. They created that metal imbalance. It's going to most often occur in cold, wet soils and high pH soils. You see it in the west on sorghum. You see it in the west on corn. In Illinois, we see it to some extent on soybeans, but it's usually pretty limited. In Iowa, they see it very extensively on soybeans. Now, there are real genetic differences in its tolerance, or in varieties' tolerance to iron deficiency. And in those areas where they know they have the problem, they really need to be selective in that, in picking the varieties. Sources of it, well, there's always sulfates of any of the micronutrients, but the chelate is going to be the most effective. And to be very honest, a foliar application is probably going to be the best approach to use with iron. That's true to some extent with virtually all of the micronutrients. Is a foliar application is going to work better because the problem exists not because most often you don't have the nutrient there, but because it's not in an available form or in the plant available form. Manganese, again, part of the enzyme system. Iron and manganese deficiency are often confused. Their symptoms are very, very similar. And some of their reactions and their functions are very similar. Again, manganese is going to occur on high pH soils. You can get it on acid soils, but it's very rare. You get, as I just said, an increase in manganese deficiency with a high pH. You You get it because of an imbalance with other metals. Again, on cold, wet soils is where it's going to show up first. Oftentimes, iron deficiency will actually outgrow itself. Once the soil warms up and dries off, the plant will often outgrow the symptoms. Again, in terms of materials that you can supply to correct the deficiency, the chelates are the most likely ones to be used, and again, a foliar application is going to work far better in most instances than will a soil application. Molybdenum, as I said earlier, is the one micronutrient that increases in pH, or increases in availability with an increase in pH. If you look at the far left side of it on an acid soil, the addition of molybdenum gives you a significant yield increase at 5.6, 5.7. Even at a pH of 6, you're getting a little bit of a yield increase. But when you kick that pH on up into that 6.2, 6.4 range, then the addition of molybdenum is very unlikely to give you a yield response. Liming programs are probably the best correction of molybdenum deficiency throughout much of the country. Zinc deficiency, high pH soils, low organic matter soils, high phosphorus soils is where it's going to show up. Zinc is involved in enzymes in the cell elongation. You're going to find that with zinc deficiency, one of the symptoms is stunting, shortening of the inner nodes. I've gotten ahead of myself, but again, where it shows up, low organic matter, high pH, sandy soils, cold, wet soils. Those are all factors that are going to lead you to zinc deficiency. High phosphorus. Now, how high do you have to be to create zinc deficiency? I don't know that we have a good number on that. We used to talk about not getting over a 100-pound phosphorus test. Now we're up to 200 and still don't have any proof that we are creating zinc deficiency out there in those fields. The place where that deficiency has occurred has been further west, out in the Great Plains, where they've leveled for irrigation, come back in with very high rates of phosphorus addition, and there they see the zinc deficiency. But they also have high pH in most of those areas as well. If the problem is due to high pH or high phosphorus, the zinc chelate is going to be a far better material to use. If the problem is simply due to a lack of zinc in the soil, then any of these materials will work well. And the inorganics, the zinc sulfates, would probably be significantly cheaper. Chloride, this is the most recently identified nutrient. I forget when it was, but it was in the 50s when it was identified as being deficient. It's involved in many energy reactions, as are most all of the other micronutrients as well. But in the Corn Belt, where we're using potash, there is no need to supply anymore. We're getting plenty of chloride out of the KCl. Now, where does the deficiency show up? It's been showing up to some extent in wheat in the plain states, areas where they have high potassium levels and don't need to supply or use potassium chloride. There they have seen deficiency of chloride on occasion. Now, we're going to move in to recommendation philosophies and a few things that I think you need to understand here and have an idea of. We could really define or put recommendation philosophies into three different categories. What many states use, the build-up maintenance philosophy, is to build the soil to a given point, that point at which deficiency will not occur, and then simply maintain it by putting back what the crop takes off. The last one, sufficiency, might be called feed the plant. Put on just enough nutrient to maximize yield for that year. Some define the first one as feed the soil, the last one as feed the plant. The one in between, the use of cation saturation ratios, or the use of CEC, base saturation, and we'll talk about each of those or that just a little bit more. That's kind of a combination of, well, I should say it's somewhat what is used in the first one, in the build-up philosophy, but when we're talking about cation saturation ratios, it limits us automatically to one set of nutrients, doesn't it? Which is that? The cations. What cations are we involved with? Primarily potassium. You cannot use a CEC or cation saturation ratio with phosphorus because it's not a cation, it's an anion. It simply will not work. I'm not sure it'll work for the cations, but it won't work for the anions, that's for sure. Now, which one of these systems we pick depends on the nutrient. Depends somewhat on the mobility of the nutrient. For nitrogen, which is very mobile, one we're not going to build up, we're all going to use the deficiency concept. We're going to put enough on to take care of the crop that year. For an element like phosphorus, which builds very easily, the build-up maintenance kind of an approach has worked very, very well. For potassium, which is kind of in between, on some soils we use the build-up maintenance philosophy, on some we use the sufficiency. We've suggested for a good many years that in those fields where you cannot get the soil test to build up, that you simply put 1 to 1.5% of the maintenance level on each year. So in that case, we're talking really more like a nitrogen recommendation. It's on an annual basis. It's to feed the plant, not feed the soil. Now, the philosophy on a buildup is to look at that point, soil test-wise, where you're going to maximize yields. Now, on phosphorus, it's going to come in at a test somewhere in that 40 to 50 pound range. You're going to optimize yield. Now, this is kind of a generalization for all crops. Actually, for corn, for the most part, you're probably going to come in at a maximum of about 30. So your odds of getting a response to fertilizer beyond that point, the other line coming down, decreases rather markedly. And what we were shooting for is to build that soil to that point at which the odds of getting a response are pretty slim. Now, when we look at the cation exchange system, base saturation, whatever the case may be, and you do need to know what cation exchange capacity means. We talked about that earlier. It simply means the ability of soils to hold positively charged ions. Now, we can measure what that is in the soil. Then people talk about base saturation. What do they mean there? All they mean is the percent of the total exchange that is occupied by any one cation. So if we say that we have 3% base saturation for potassium, we simply mean 3% of whatever the exchange capacity is of that soil is occupied by K. Or if we say we've got 40% of the exchange occupied by calcium, it simply means 40% times the CEC. And that's how many milliequivalents of that particular cation you're going to have present in the soil. Take percent base saturation times CEC gives you the number of milliequivalents of that nutrient that you have. So, yeah, and then take that number times pounds per milliequivalent, and it'll tell you how many pounds per acre of that nutrient you have. Now, in reality, when a laboratory determines the K level or the calcium level, they are determining a concentration. That concentration could be given in parts per million or it can be given in pounds per acre. But that's what they're actually determining. When they report to you that it's such and such of a percent base saturation, they go backward through this set of equations to get back to that percent base saturation. So the first determination is one of concentration. And then they figure out what the exchange capacity is by simply adding these concentrations up. And then they convert back and look at what the percent base saturation will be for each of them. It's a mathematical manipulation. This is a very important conversion for you to know. Pounds per acre is equal to parts per million times 2. An acre furrow slice, a plow layer slice is the way we've used to describe it, 6 2/3 inches deep, will weigh 2 million pounds. So if they tell us that we have X number of parts per million, let's say they say we have 10 parts per million, how many pounds per acre is that? Well, if that furrow slice weighs 2 million, we have 10 parts per 1 million, simply take it times 2. We've got 20 pounds per acre of whatever element we're talking about. So ppm times 2 equals pounds per acre, or pounds per acre divided by 2 equals ppm. And that is important to know, not only in preparation for the exam, but in many of your day-to-day operations. Okay, we're going to wrap up here, and I've already gone about 15 minutes into Emerson's time, but he'll extend your time this afternoon, I'm sure, to take care of that. We're going to run through the nutrient deficiency symptoms real quick. Nitrogen, again, remember, it's on the lower, older tissue. It's going to start at the tip and move up the midrib. N for nitrogen. Nitrogen, as we said, is mobile because it's on the old tissue. Phosphorus is going to occur on small plants. Seldom do we ever see it on plants that are knee-high and higher, unless you have an extreme deficiency. It's going to occur usually early in the spring when soils are cold and wet or cold and dry. And it shows up as a purpling of the leaf. Potash, again, an immobile nutrient, a mobile nutrient, because it's showing up in the old tissue, and it yellows along the margins of the leaf. So it's okay for potash. It's really not okay to have the deficiency, but remember it is okay outside for potassium. The outside of the leaf is where the deficiency will show up. On soybeans, the same is true. It'll be on the margins. And the center of that leaf will stay green for quite some time period. Just a little closer look at it. Calcium deficiency, remember one of the functions of calcium deficiency is cell elongation, cell division. The deficiency shows up as the buggy whip or the onion leaf. The top of that plant doesn't unfurl. Now there are a lot of other things that can cause that to happen as well, aren't there? Some herbicides can cause that same kind of a problem. But that is typical calcium deficiency. That shot was actually taken in Illinois on an acid sand up in Kankakee County. Magnesium deficiency. What's one of the functions of magnesium? What's the one? Chlorophyll formation. Part of the chlorophyll molecule. So what would you expect? You'd expect yellowing. And that's what you get. And as I said earlier, as the deficiency continues for corn, you'll get a maroon or a purpling of that leaf. On soybeans, and I've never seen this myself, but they tell me that's what the deficiency looks like. Again, the chlorosis, the yellowing of the leaf, the purple spotting around the outside edge is typical of magnesium deficiency on soybean. Sulfur deficiency. The easiest way to tell sulfur deficiency is to have a sulfur-sufficient plant beside it. It's very, very difficult to tell, to be very honest, when you're on a whole field basis. The deficiency will occur as a yellowing in the upper part of the plant, which means it's what? Mobile or immobile? Immobile. It's not translocating. And it's that yellowing. It's the the same kind of yellowing you'll get with N, except N's going to be on the bottom, sulfur's going to be on the top. You'll get some stunting of it as well. Manganese deficiency, a chlorosis, and it's going to occur on soybeans. That's the one you're going to see it on most often. You're going to get yellowing, but the veins are going to stay green. It will eventually get this rusty appearance. Look like little rust pustules on there, like a disease. But when it first starts out, that rusty appearance is not going to be there. Now, in contrast to iron, iron is going to be chlorotic as well. You're going to get that yellowing, you're going to get the green veins, but the difference is iron is not going to give you that rusty appearance. Iron is going to go white. You'll often see those leaves just plain turning white. And that's the way I distinguish between the two. Boron deficiency, what crop are you going to see it most likely on? Alfalfa. Seldom do you ever see it on corn or soybeans. Shows up as a stunting or rosetting in the upper part of that plant. See, those leaves are coming out just almost one right on top of the other. That's not a normal plant. It'll also show up as a yellowing and eventually a purpling of the upper part of that plant. Now, the yellowing and purpling looks, particularly the purpling, looks very much like leafhopper. The difference is with leafhopper, you'll get that V shape coming in from where the insect bit into the plant. It'll purple back in a V. With boron, that won't be the case. Boron deficiency is often confused with dry weather because it occurs at the same time. Why is that happening? Why would you expect it to occur at that time? Well, dry weather, where are you getting your water from? What water you have, you're getting it from down deep. Boron is primarily coming from organic matter. Organic matter is going to be up top. So you're not going to have the boron supply down there where where it's rooting. Molybdenum deficiency, not any good characteristic symptoms that I know of. It's just on an acid soil, you're going to get stunting, small puckered leaves, but there's no coloration that I'm aware of, at least throughout the plains. Zinc deficiency, and unfortunately I don't have a good slide of it, but let me describe to you what it looks like. There are three characteristic symptoms of zinc deficiency. Number one, stunting or rosetting. You'll find corn leaves just popping out one right on top of the other with zinc deficiency. Number two is the whitening of the leaves. The leaves will basically turn white near the base of the stalk. But before it turns white, the third symptom, but the one that will occur before the whitening, is the one that's typical of every micronutrient, and that is chlorosis. You'll get a yellowing. The veins will stay green for a little while, but you'll get that yellowing. And then it will proceed on to give you that white coloration at the near the base of the stalk, near the base of the leaf, right where it attaches to the stalk. So stunting, the whitening, and the chlorosis. I think that was in fact it was the last slide that I have. I do want to just make a couple of comments for those of you that are planning on going in and taking the exam. Spend a little bit of time reviewing, but don't panic over it. Most all of you know the material and know it well enough that I don't think you're going to have any problem. But sit back and review a little bit. When you go into the exam, remember how to take exams. As you go down through the questions, read them. If you quickly identify the answer, answer it, and go on. If it's a question that doesn't really click with you, go on anyway. Don't sit there and spend a lot of time on that particular one. Go on through and do the ones that you know first, and get those done, and then come back and do those that you had a little more difficulty with right at first. Test people tell me consistently that your first impulse is almost always the right one. When you read those answers, and it's a multiple choice, that one that sounds the most logical to you right at first is probably the right one. And you're probably best off to stick with it. But again, sit back and relax, sit back and study a little bit, and look through some of these references that we've given or we've suggested to you, and you're all going to do very, very well, I'm confident.